All right, for the last chapter that we're going to do together in AP Stats, I thought let's go easy. Let's do some second grade math games. What do you guys say? You guys want to do some second grade math games as your last chapter in AP Stats? That sounds like a good idea to me, right? I mean, sure, let's do it. Wah, wah. Oh, here's me. I'm Lucy with a me mustache, and there's you. Yeah, we're not gonna quite. Oh, here, we can even do something extra here. Second grade math. You're going for the second grade math? Bloop. I pull it out from you. Booyah. We're going to do chi-squared distributions instead. I mean, that sounds just like second grade math, right? Chi-squared distributions. It's totally second grade math. Look at the colors. Yeah, look at all the colors. Colors like second grade. Sure. Now, suppose you open a bag of M&Ms and discover that there's only one blue M&M. You might not think anything of it, but the next time you open up a bag of M&Ms and you count the number of blues, I guarantee you will think of this chapter. You're welcome. The company claims that there are supposed to be 10% blue. So you count all the M&Ms in your bag and you have 56 total M&Ms, yet you only got one blue M&M. Now, how many blue M&Ms should we have expected to receive? Well, if there were 56 M&Ms total and we expect 10% of them to be blue, well, that would be, what, like 5 or 6? 10% of 56 would be 5.6 exactly. We can't really have a decimal point number of blues, though they could, like, give us half an M&M, I guess. So we would expect, 5 or 6 blue M&Ms, but we only got one. Now, is one far enough away from 5 or 6 that we would expect something to be off? Maybe, maybe not. That's what we're going to discuss this chapter. So we could test if only one blue out of 56 is significant by performing a 1 proportion z-test like we did in chapter 9. So we could say the proportion of all blue M&Ms is 10% versus we feel it's less than 10%. If we were incorrect about the number of blues, we must be incorrect about other colors as well, right? If we got shafted on the blues, that means they had to have filled the bag with more of another color than what we would have expected. So we could test the proportion of each color to see if the company's claims are accurate. So we could do a hypothesis test for blues. We could do a hypothesis test for yellows and greens and browns and reds and oranges. So in the end, we're doing 6 hypothesis tests, which doesn't really sound like a whole lot of fun. Now, this process would be very inefficient. It would also not tell us how likely it is that all 6 sample proportions differed from what they were supposed to be. There is a single test that can be applied to see if the observed sample distribution is different from the hypothesized population distribution. And this is specifically called a chi-squared. It kind of looks like an x squared, but it's really like a fancy looking x squared goodness of fit test. And this is what we're going to do in the next video. A chi-squared goodness of fit test. Okay. Now, other places you might use a chi-squared goodness of fit besides testing M&M colors. We could be talking about the colors in a box of Trick cereal to see if they're, supposedly what the company says that they put in there. And we're going to look at a problem that focuses on another kind of goodness of fit type test. So some things about chi-squared distributions you should know about. They only take positive values. So before, when we did z or t tests, we could have ended up on the left side of the distribution and had negative values. But we don't have to worry about that now. We will only end up with positive values. And every chi-squared distribution is skewed right. A chi-squared distribution is specified by one parameter called degrees of freedom. So that's nothing new. We still have this concept of degrees of freedom. So there will be different looking chi-squared distributions depending on the number of degrees of freedom. The total area under a chi-square curve is 1 or 100% still. Each curve technically starts at 0, but if you look at this degree of freedom 1, it doesn't really look like it starts at 0. It does, it's just so teeny tiny squeezed in here, you can't really see it. So if we wanted to, just to be maybe a little bit more precise, we could take this 1 degree of freedom 1, and technically it slithers back down the vertical axis here. Um, so each one begins at 0 on the horizontal axis, increases to a peak, and then approaches the horizontal asymptotically from above. So we never really touch the horizontal axis here. It just starts to approach it, but never really fully touches it. As the number of degrees of freedom increase, the curve looks more and more like a normal curve. So notice 1 degree of freedom, 2 degrees of freedom, 8 degrees of freedom. As our degrees of freedom are getting larger and larger, this thing is starting to normalize more and more. How many degrees of freedom does it take before it looks like a normal curve? Don't really know. We don't really care. Each curve has a mean equal to the number of degrees of freedom. Okay? So the mean, and this isn't necessarily the peak, but here, let's go ahead and talk about it. The peak is located where degrees of freedom minus 2 is located. So right here, this would be the peak of this curve. And this would be at, if this is 8 degrees of freedom, this is at 6. So we'll say the mean right here, this would be kind of the balancing point, if you will. This is where 8 degrees of freedom is located. 4 degrees of freedom, that means right here at the peak, this is 2. And this is, I don't know, maybe 4 right here. There's where the mean is located. Now, the part to really know would be kind of where is the peak located? And that's always going to be the degrees of freedom minus 2, given you have at least 3 degrees of freedom. If we only had 2 degrees of freedom, then the peak would be at 0, and that wouldn't make too much sense. If we had 1 degree of freedom, like this one here, the peak's not really going to be at -1. So really, with degrees of freedom being greater than or equal to 3, does that apply? Okay. Now, a definition of the chi-squared statistic. Okay, before when we did hypothesis test, if we were doing a proportion problem, we were solving for a z value, a z statistic. Or if we were doing a mean problem, we were solving for a t statistic. Now we're going to be solving for a chi-squared statistic. And that is going to be a measure of how far the observed counts are from the expected counts. And this is going to be our lovely formula we're going to use. Basically, what it's saying is we are going to add up, that's what our sigma here represents, capital sigma. We do have a lowercase sigma, which represents our population standard deviation. But a capital sigma, we're going to add together all of the differences of our observed and expecteds, square them, and then divide by the expected count. Okay? For example, if we were looking at the M&Ms, all possible values that I mentioned here is that where the sum is over all possible values of the categorical variable. All possible values means we're going to have to do this for each color. And then we're going to add together all those results to get the overall chi-squared value. So the example we're going to look at together. A new casino game. Grab my pen here. A new casino game involves rolling 3 dice. The winnings are related to the number of 6s rolled. Suppose you play the game 100 times. The casino becomes suspicious of your rolls and wishes to determine whether the dice you are currently using are fair. So we're going to write some hypotheses, determine all the expected counts, and calculate the chi-squared statistic. So first off, our hypotheses. Now, that is that all 3 of our dice are really fair, that each side truly has a 1 in 6 chance, if we're talking about a 6-sided die. Our alternate hypothesis, I should rather say, is that at least one of the dice is not fair, that there is some side that does not have a 1/6 chance. Now again, do we know if it's going to be for 1 die, for 2 die, or for all 3 dice? No, but we know something is wrong overall. Okay, and there's no way we're going to know if 1 dice is bad, if 2 dice are bad, or if all 3 dice are bad, unless you do 3 individual hypotheses tests, 1 for each die. Okay, so this is really an all or nothing thing. Either they're all fair, or we're just going to have to say in general that something's wrong, at least one of them's not fair. We don't know which one, but that's the way we have to leave it as. Now, believe it or not, doing some Googling on dice, trick dice, there's a rapper named Trick Dice. Did you guys know this? I did not. And I like his middle album here, Fully Loaded. What an iconic name for an album when your name's Trick Dice. I mean, I would make all my album names something related to Trick Dice. But no, he goes bar none, fade all. Like, what does that even mean? I don't know. Uh, like a drill. What's that mean? I don't know. It's just craziness. Like, Trick Dice, stick to your middle album here. Make it more mathematical. That's cool. All right. Now here's what actually happened. This person rolled the die or rolled the 3 dice 100 times. 48 times he got no sixes. 35 times he got 1 6 to show up. 15 times he rolled 2 6s. And 3 out of the 100 times he rolled 3 6s. Okay? Now these probabilities here, don't worry about how I got these, but these are the probabilities. Basically, I had to use a binomial distribution, which, if you remembered, used our combinations. So for like this 0.5787, combination 3, 0, and then probability of rolling a 6 would be a sixth, and we want 0 of them, and not rolling a 6 would be 5 6, and we want to roll 3 of those, and that's how I got this number. So you're not going to be expected to come up with these probabilities, but that's what I had to do to get them. Something that we have done before. All right, now back to the drawing board. So these are observed counts. This is what we saw from basically our sample of rolling the die 100 times. And notice all my probabilities do in fact add up to be 100%, so I'm not leaving anything out. Now the expected number. We've done expected stuff before, it's just been a little while. We did expected counts when we did that scratch-off lottery ticket thing. And we would take the amount of money you could win times the probability of winning that. So all we did was we multiplied the probability times what we wanted to see happen. Okay, so our expected counts here, how many times would we expect to roll 0 6s? Well, we take this and we multiply it by its probability, which this ends up being nice. We would expect to roll 0 out of these. Is that right? That doesn't sound right, but... All right, brain fart, scratch that. This is what I meant to say. If this is how often 3 non-6s come up, and we're going to roll 100 times, this is what I meant to say, then 100 times this probability means we would expect 57.87 out of 100 rolls to produce 0 6s. Likewise, if rolling 1 6 happens 34.72% of the time, then in 100 rolls, we would expect to see 34.72 out of 100 times to come up with 1 6 out of 3 dice. Similarly, to roll 2 6s out of 3 only happens 6.944% of the time. And out of 100 tosses of the dice, we should expect only 6.944 of these 100 rolls to produce 2 6s out of 3. And last but not least, to get 3 6s in 100 rolls of a die, we would expect would only happen 0.4630 times. Not even really one time would we expect that to happen in 100 rolls. Okay? It would take more like 200 rolls before we would finally expect to see triple 6s to occur. And this happened 3 times for this person. So you can see why maybe the casino would be a little suspicious. They wouldn't really expect it to even happen 1 time out of 100 throws. And this dude got it 3 times. So you can kind of see their suspicions happen. Now, if we add all these up, we should get 100 here. And if you want to add all those up, that's fine. Are you going to get exactly 100 out of this? Probably not, but it's going to be very, very, very close to 100. So if we just wanted to check real quick, we could do that. Let's see, where's my tools? Tools, math tools, calculator. 57.87 plus 34.72 0.72 plus 6.944 plus 0.463 equals 99.997. That's the type of thing you're going to see, which is essentially, it's just rounding. We chopped off some numbers here rounding, and that's why we lost our 0.003. So if you don't get exactly 100, but you're very extremely close, that's cool. Now, to get these values, and this is where the formula came into play. Let me jump back here, this part. We need to take the observed minus the expected, square it, divide it by the expected, and then add all of those results up. Okay, so there were 4 possibilities here for 6's. So we're going to have to do that 4 times and then add all 4 of those things together, and that is our chi-squared statistic. So on this part, we're really going to take 48 minus 57.87, square it, and then divide by the expected, 57.87. For this one, we're going to take 35 minus 34.72, square it, divide it by 34.72. 15 minus 6.944, square it, divide it by 6.944. And last, 3 minus 0.463, square it, divided by 0.463. All right, so now let's get some numbers here. And we're obviously going to want to round these a little bit. Should we just use our calculator here? Why not? Okay, 48 minus 57.87 equals, square that, divide by 57.87. 1.683. I'm just going to do 4 sig figs here. 1.683. All right, let's continue on. 35 minus 34.72 equals, squared, divided by 34.72. Ooh, teeny tiny number. 0.002258. 0.002258. Number 3, 15. Oh, 15 minus 6.944 equals, squared, divided by 6.944. 9.346, we'll say. And last but not least, 3 minus 0.463 equals, squared, divided by 0.463 equals, ooh, big number, 13.90, basically. Now, if I add up all these numbers, 13.9, 13.9 plus 9.346 plus 0.002, oh, there's an extra, go back, 2258, geez, oh Pete, why is that doing that? 58, there we go, plus 1.683, 24.93. So this 24.93 is our chi-squared statistic. This is the number that we're going to use in a calculation in the next part of the process that we're not going to do in this video. But as long as you can get to this point, you are good so far. Now, kind of a follow-up question we can look at here is, which one of these things contributed the most to the chi-square value? Now, if things were really okay, if those dice that we were rolling were perfectly fair, we would expect each one of these chi-squared numbers to be 0, 0, 0, 0. If the observed and the expected are expected to be the same, then every time we subtract these two numbers, we should expect 0, and 0, and 0, and 0. So if everything was ideal, then our chi-squared value would be nothing. Okay? And so whenever we find a probability that's greater than 0, it'd be 100% of the time. We would expect that to happen. Now, what we want to look for are the largest, and we can also look at the smallest, chi-squared individual parts here. So this 13.90, rolling the 3 sets of triple sixes here, was the most unexpected thing to occur. It contributed really more than half of the total chi-square value. 13.9 out of 24.93 is over 50% of that value. Okay, and that is a big chunk. Now, what was the most or the least unexpected thing to occur? Well, that would have been this 0.002258. We rolled 35 single sixes when we expected to roll 34.72. So this is the closest thing to what we expected to truly happen, assuming the dice were fair. So they always like to ask follow-up questions like that. Like, what was the one thing that contributed the most to the chi-square statistic? And you're just going to be looking for the one value that has the largest out of all of them. And they could also ask, consequently, what contributed the least to the chi-square distribution? And that would be your smallest number here. Now, for those watching the videos, you need to do this problem and bring it to class with you. This isn't an option anymore. This is do this problem and bring it to class because I am checking it for homework now. That is all. Good luck, and we'll see you in the next video.